This is the second lecture on the theory of conjoint measurement, additive conjoint measurement. You will recall in the previous lecture we discussed the case of two components, and in this lecture we're going to do two things that are fairly closely related to the previous one. The first thing we will do is generalize the theorem from 2 to n components where n is greater than or equal to 3. And the second thing we will do is quite distinct from that, is go back to the two-component case and talk about what happens when the data are provided in numerical form rather than just in qualitative form. There are some advantages that one can take if the data are in numerical form. I'm assuming they're in numerical form but not conspicuously additive. All right, to go to the generalization to n components, let me remind you of the gist of the theorem for two components. It was that you have an ordering on the Cartesian product of two components, and if it satisfied the following properties, then an additive representation exists. First, a property called independence that permitted us to induce a weak ordering on each of the components. Of course, I'm assuming the ordering is a weak ordering. The independence induces an order on each of the components separately. Secondly, we had to assume a property that was called double cancellation, or actually we could get away with a slightly weaker property, the Thompson condition. Then we had to assume a form of solvability called restricted solvability and an Archimedean property. Now, we can discuss in the two-dimensional case the independence property graphically, and it's a form that is frequently used in presentation of experimental data. Suppose we plot a dependent variable depending on both components, numerical variable, and let us represent one of the components by the x-axis, and we'll have two levels on that component, say A and B, and the second component on one level, for example, produces these data points. We'll call that level P. Now, if it turns out that at level Q the data points cross in this fashion, everyone knows that that rejects an additive representation. And that's standardly used to throw out additive models experimentally. On the other hand, if you get the data looking in this fashion, and if there are in fact many more than two levels, but this is the presentation just of two, it's not immediately clear whether the additivity is rejected or not. And in this two-dimensional case, it's essential that one look at the property of the Thompson condition, since that is also required in the axiomatization of the additive representation. And in general, in empirical context, that has not been studied, although in recent years people have become more aware of it. Now, when we turn to the 3 or higher dimensional case, it turns out that we're not going to have quite the same picture. It frequently in mathematical structures, going from 2 to 3 changes somewhat. And let me try and describe the situation with n factors. The first thing we have to do is introduce the definition again of independence when you have more than 2 factors. And there are 2 ways one can think of doing it, and I will present one of them. And that is to say we'll look at every subset M of the set of the first n integers, which I'll call capital N. And now consider that I've selected a particular set of elements in the complementary set n minus m. So outside of the set I'm interested in, the set of indices m, I select a particular value there, and having done that, the given ordering on the whole Cartesian product of n factors induces an ordering on the m factors. It, of course, is in general dependent on that particular choice of values outside of the set of factors that I'm interested in. Now, the assertion of independence is that it, in fact, does not depend on that choice. That is, for all choices of vectors in the n minus m components, whether it be this A one or a B one, a different one, the induced ordering is exactly the same, and one then suppresses the choice outside of the set M. And that is the notion of independence. It generalizes the notion we had for two factors. If I specialize this for n equal 2, I get the old definition back. Now, it does assume more than is needed in order to just induce an unambiguous ordering on each component separately. See, we've induced an unambiguous ordering on every subset of components, not just individual ones. Now, one at this point, when you first attack the problem, think the next step was to try and figure out a generalization of the Thompson condition. We needed that in the two-dimensional case. Presumably, we should get it in the three-dimensional case, but that turns out not to be necessary. Lemma 614 in the text states the situation in the following way. Suppose that the conjoint structure on n components satisfies the weak order condition, independence as I've just defined it, and restricted solvability, which I'll later specify it's the obvious generalization of restricted solvability in the n equal 2 case. Then the subsystem, any of the subsystems involving two components with the induced relation that is induced via the independence definition, in fact satisfies double cancellation. So what we're saying here, let's make clear we understand this lemma, that once you have three or more factors and this strong form of independence on those factors, that forces on each of the two-dimensional subsystems the double cancellation property that was needed in order to get the additive representation. Now, the proof given for the case of restricted solvability is rather laborious. In the case of unrestricted solvability, the proof is very simple, and I think I'll go through it. So I'll assume unrestricted solvability, and I'll just assume three components. The thing obviously generalizes. And so the supposition is now on, let's say, the first two components, we're going to check for double cancellation. So we assume the two necessary inequalities or antecedent inequalities for the double cancellation property. AX is greater than or equal to FQ, FP is greater than or equal to BX. You remember that involved the F's on both sides of the inequality and the X's on both sides. Now, select any element U in the third component and solve, and here's where unrestricted solvability comes in, solve for V in this equation. You'd have Fx and AXU, all of those are known, and now you solve for this V here to make an equality. By equation 1 and independence, I can put the same element on both sides of this inequality, and it'll hold in the three-dimensional case. In particular, let me put U there. That gives me equation 4. Now, combine equations 3 and 4. You see that this term and this term are identical. Therefore, by the transitivity of the ordering, you get Fxv greater than or equal to Fqu in this equation. Now we can apply independence. We've got a common term here. We can replace it by any other common term. And in particular, let's replace it by V, giving us this equation. Now go back to hypothesis 2. We haven't yet used that. And by independence, we may add v to both sides of that without altering it. That gives us equation 7. And then we combine 6 and 7, and you see this term is the same as that term. Therefore, FPV is greater than or equal to BQU. Once again, we will use independence in equation 3, and we will replace x, which is common on both sides, by another value, namely p. When we do that, we get equation 9. And now, if you look at 8 and 9, you see that you have the FPV term common, so by transitivity, APU is greater than or equal to BQU. And then, of course, using independence, the induced relation on the first two coordinates is AP greater than or equal to BQ, which is the property of double cancellation. Now, as I said, it can also be proved in the context of restricted solvability, but the proof is significantly more complicated. As you can imagine, the problem is that you don't always have the solutions you want when you want them in the case of restricted solvability, and you have to work around that difficulty. All right, then the theorem that can be proved in this case is, as you would expect, that you're not going to require any form of double cancellation. So what you assume is a weak ordering, the independence, restricted solvability, and now let me be explicit what it says. It's just what you'd expect it to say. That is, you're given a particular element, A1 through AN, and you're given that for a certain choice of Q1, Q2, and Qn, except on the ith coordinate you have something special, and I'll call it B super bar, is greater than or equal to the n tuple of A's. In turn, that is greater than or equal to the same Q's, except in the ith position there's an element that's I'll call Bi lower bar. And this is to be true for each I now. You've got, the statement of this is for a particular I, but and the conclusion is that then there exists a BI in capital AI such that, in fact, strict equality holds. And this assertion is true for each of the different components I. So that's the very natural generalization of restricted solvability. The Archimedean property is the usual one. Every strictly bounded standard sequence is finite. And the fifth one simply requires that three of the components, or three or more, be essential. If you're in a degenerate case where only two of them are essential, then the problem reduces to that of the two-component conjoint case, and you would need the Thompson condition. You would not be able to prove the Thompson condition for the pairs in that case from independence. Now, given those assumptions, the assertion is that there are mappings phi from AI into the reals such that their sum is order preserving, and if phi prime is another set of mappings whose sum is order preserving, then they're related in the usual linear fashion with a common unit. That is, there's a single alpha greater than 0 and beta i's corresponding to each component such that phi prime is alpha times phi plus beta I prime. So they're linear transformations with a common unit. Now, the proof of this is not entirely trivial, but the general strategy of it is easily outlined. What you do is consider any pair of components. By lemma 614 and the theorem for the case of two components, one is able to construct an additive representation of that pair. Now, that means in essence that you produce, let us say, on the ith coordinate, a pair of, you have a scale I'll call phi sub ik, which is the scale that is induced by working with the pair, ij, working with the pair ij. Now, if I instead work with the pair ik, I induce a different additive scale that will enter into an additive relation with, on the kth coordinate, something that it was conditional on working with I, just as in this case I will be working with an additive representation that I can denote that way. So the first index on these representations denotes the coordinate you're dealing with, and the second one denotes the coordinate that was used to match it. Now the question is, do these two relate to one another in any simple way? And the answer is yes, they do. They're in fact linearly related. And the way one shows that is to use the operation, the extensive operation that's induced on A sub I from the ordering on the Cartesian product with J and then with K. And you're able to show without too much difficulty that those are in fact identical operations. And thus the uniqueness theorem for the extensive structures forces these induced scales to be linearly related. And from that, then it's easy to show that you can make a collection of n scales, one for each component, such that any pair of them is order preserving for that sub-component. The rest of the proof then is simply to show that their sum is in fact order preserving. But this is the mechanism really of constructing them, and it does rest entirely on understanding that the general concept of independence in the n-dimensional case forces double cancellation on the pairs. So that's the theorem that generalizes it. There are various specializations of it discussed in the book, which I will not go into in this lecture. Let us turn now to the question of what additional help we can get in the situation where the data are presented to us, the conjoint measurement data are presented to us in numerical form. This happens fairly often in experimental situations in two different ways, and there are two separate developments that would go along with each one. The first one, the case one that I'll talk about, has as examples things of the following sort. First example, let us denote by X, a real number, the intensity of a signal that is being presented to the left ear, and Y, the intensity of a simultaneous signal or tone to the right ear. And let us denote by F of X, Y, the mean reaction time to respond to that signal complex, so that the subject is sitting and waiting to respond. Simultaneously, tones come to the left and the right ear, and he is to respond as rapidly as possible, and F of X, Y is the mean reaction time. So everything is numerical there. It's but it's typically a conjoint measurement situation in the sense that you've got two components and one dependent variable, and that dependent variable, of course, induces an order on the product space of the intensities to the two ears. The second example, let X denote the age of a person, let Y denote the weight to height ratio of that person, and let F of X, Y be the probability of his having a heart attack in the next year. Again, everything is numerical, and it is definitely a factorial situation of the conjoint sort. So abstractly, I want to then consider the following general situation. There are scales X from the first component into the reals, Y from the second component into the reals, and a function F, capital F, that maps the reals, or it'll turn out really subsets of the reals, into the reals, such that the ordering in the conjoint case is represented by or usually induced by is in practice that you don't have the ordering given independently of its induction through this numerical function f. But in any event, you can think of it there being an ordering holding if and only if the f is corresponding to, let me just restate it. The AP is greater than or equal to BQ provided f of the numerical measure associated with A and y, the numerical measure associated with P, is greater than or equal to the f applied to the numerical measure associated with B and that associated with Q. Now the question is there some way, some easy way of telling whether this is an additive structure? I mean, we could, of course, induce that ordering and operate on it using the fundamental theory of conjoint measurement, but the question always arises when you're dealing with these numerical functions, isn't there a simpler way of answering the question whether there's an additive representation? That is, the question is, can we find functions little f, f1, and f2 such that when you apply little f to capital F, that will permit it to be represented as f1 of x plus f2 of x. And that is an additive representation, of course, of that ordering induced by capital F. And I'll call that relationship star. That is a classic problem that was raised in the statistical literature and was solved in the 1930s, if I'm not mistaken. The theorem is stated as theorem 6.4 in the text, and it reads as follows. We'll assume that the function f is defined on the numerical Cartesian product onto an interval z, and we'll assume these are all open real intervals. Moreover, we'll assume that the partial derivative of f, the second partial derivative, exists, and that f of x, the first partial derivative, times the second partial, the two first partial derivatives, the product of the two first partial derivatives are not equal to 0. Or put another way, neither first partial derivative has a 0 anywhere. The assertion then is that the equation star, this additive representation over here, holds with function f such that its second derivative exists and its first derivative is non-zero. These are restrictions that are necessary to avoid the ambiguity of dividing by 0, and also in order to you have to have the derivatives existing for the kind of proof that we'll see. That holds if and only if there's an integrable function g that maps the interval z on which the image of f into the reals, such that the second partial of f divided by the product of the two first partials is a function only of f itself. And if that's the case, then the functions little f and f1 and f2 are given by these explicit formulas in terms of g. That is, once you know what g is, then you can compute this function, and having computed that function, you down here have to compute its derivative, substitute it in here, and carry out that integration, and you get an expression for f1, and then f2 is simply the f expression less the f1 expression. Now let us see why that is so. The necessity argument goes as follows. Suppose the equation star in fact holds. We compute the partial derivative of that equation with respect to x. By the chain rule, that gives us the derivative of little f with capital F as the argument, and then we have to take the derivative of capital F with respect to x, so that's the partial capital F with respect to x. And on this side, we simply get the first derivative of f1, and this, depending only on y, vanishes. Now we take this equation and take the partial with respect to y, and you get the this is a product of two functions here, so you get the one function, f sub x, times the derivative of that, which is little f double prime, evaluated f, and then using the chain rule, you have capital F the partial of that with respect to y, plus then the other term, which is f prime of f times the partial of this with respect to y, which is the second partial. And this, of course, is a function only of x. I'd better make it explicit. So taking this partial with respect to y gives 0. And now if I rearrange this equation, which I can do because by my assumptions this is not 0 and this is not 0, so that then rearranging it I get this term, this divided by that, is equal to minus this second derivative of f divided by the first derivative, which can be expressed as minus the derivative of the logarithm, and that's a function only of f itself. And that's the condition that we stated was necessary and sufficient for this representation. And once you have this expression, now you integrate it in order to get this form, and then direct substitution leads into these equations without any difficulty. The reverse of the argument, the sufficiency, proceeds as follows. F1 is of this general form, where the z here, well, I really should call this x. It's the first argument. What I'll do is just look at this without the integral and show that this whole thing is a function of x only, therefore the integral can be a function of x only. So I look at this, and to show that it's a function of x only, what I want to do is take the partial derivative with respect to y and establish that that partial derivative is 0. So the partial derivative of this with respect to y is fx, then the second, now taking the derivative of that, it's the second derivative evaluated at f times the partial of f with respect to y, plus then the other direction, you get this term here, and the partial of f sub x with respect to y. Now we don't yet know it's 0. That's what we want to show. We now use our given hypothesis, this hypothesis. We state that here, and by equation 6, from equation 6 we can compute what g of f is, and it's easy to show that that's minus f double prime over f prime, and that, when substituted into here, forces this to be 0, giving that f1, as expressed here, is in fact a function only of x. It's not obvious when you look at it that that's the case. It might depend on y, but this shows that it doesn't. Now, if I look at f2, which is expressed this way, I need to show that it's a function only of y. So what I do is take the partial derivative of it with respect to x, and that is given by this, and this in turn, what I now have to do is take this expression and compute its derivative. Well, when we take the derivative of that, it just kills the integral sign, and we put that in, and you see that you have the same thing, so it's equal to 0. And that means then that equation 8 depends only on y. And that then completes the proof of the result. So that if you are in the situation of having a numerical representation of the data, and if the functions are known analytically, which often means that somebody fits analytic functions to empirical data, then you can solve the question of whether there is an additive representation of those data in a very simple manner. It's comparatively easy with analytic functions to check this formula and to compute these representations. On the other hand, if the data are not fit in analytic form and they are simply tabled, this is of relatively little direct assistance, and one has to really go back to the constructive devices that are involved in the basic qualitative theory, namely the standard sequences. Those are really the way that one has to go about constructing such a function. There's an example in the literature where that has been done. It's a paper by Lefelt and two Dutch colleagues in which they took empirical data on loudness judgments where the intensity of the sound to the two ears was varied, and actually constructed standard sequences in order to see whether there was an additive representation. The second way in which numerical data often arise for conjoint structures is in the form of indifference or trade-off curves. I'll give a couple of examples. The first one might be that you performed an experiment involving animals that have to select between alternatives where each alternative is characterized by a certain amount of food reward and a certain delay in receiving that reward. And one can seek out the locus of pairs of amounts and delays that produce equivalence, that the animal is indifferent between the two alternatives. The second example are the very commonly discussed indifference curves of economics. And in general, a great deal of scientific work describes the trade-offs between two and sometimes more variables. And you can always think of those trade-offs as being represented as one variable y as against another, and you have a locus of points that are all judged indifferent to one another. Another kind of example are the equal loudness contours that I mentioned in discussing the solvability condition in the last lecture. In terms of the previous numerical representation of capital F of x and y, where f represents a numerical dependent variable, what we're seeking out here, what we have available, is the set of pairs xy such that f of xy is a constant. Or we may rewrite this in the form of expressing y as a function f sub lambda of x whenever f of xy equals lambda, and the indifference curves are of this character. And so the question now that can be raised is that given a family of indifference curves, that is, functions f lambda of one real variable against another, where little lowercase lambda lies in some index set, and here I've only got 3 curves. I might have a continuum of curves, depends on the situation. The question is, when is it reasonable to suppose that these indifference curves arose from some function of 2 variables being set equal to a constant, and that function is capable of being transformed into additive form, so that you have f of lambda, which of course is another constant, call it c. Little f is applied to capital F and yields an additive representation. And so the issue is, when can you think that your indifference curves have come from that kind of structure? Now, it's clear from this sort of equation that if I've transformed the variable x to f1 of x and the variable y to f2 of y, then in the transformed plane, these are straight lines, and you have indifference curves that are parallel straight lines. So the issue is, when can I transform a system of curves here into a system of parallel straight lines? The general statement of what's involved for this to be done is caught in the following definition. we'll say that a family of strictly increasing scales, there's a convention matter here whether we're dealing with decreasing or increasing functions. Usually people draw indifference curves, as I have, as decreasing functions, but it's quite trivial to transform the whole thing into a discussion of increasing functions, and that's the way the literature has been cast, so I'll treat it that way. So we have a family of increasing scales, and we're going to call that family uniform if and only if there is an increasing function phi such that the new family of scales that is generated by taking phi inverse of the argument and then applying f lambda to it are parallel in the following sense, that given two indices lambda and mu, there exists a constant that depends on lambda and mu such that in the transformed domain they differ simply by a shift. The only difference between the scale at lambda and the scale at mu is a shift in the argument, so that these kinds of functions, they're increasing and they are parallel to each other in the sense that there's a constant displacement between them. If this is the lambda scale and this is the mu scale, then this constant is k lambda mu. And in that situation, if the scales exhibit that property, then I claim they can indeed be transformed into parallel straight lines, and the proof proceeds in the following way, that that's true. Select one of the phis. There may be several phis that will do this job. Select one of them and call it phi 1, and define the family G lambda to be f lambda phi 1 inverse, and select any lambda 0, and we'll just hold that fixed, and define phi 2 of y to be G lambda 0 inverse. They're increasing functions, strictly increasing functions, so their inverses exist. And you take G lambda 0 inverse of y and call that phi 2 of y. Now consider any indifference curve, y equals f lambda of x. Phi 2 of y at that point is G lambda 0 of y, but for y we replace by f lambda of x. And then I can put in phi 1 inverse phi 1. That's simply the identity, and it doesn't do anything. On the other hand, I now will group things this way, and so I have as the argument phi 1 of x, and this, of course, is what I've defined to be G lambda, so I have it in that form. But now recall, in this family, the things that I've been calling the G's are parallel in the sense they differ only by a displacement. So I'm in that situation. This G lambda differs from G lambda 0 only by a displacement, so I substitute that. Now these are inverses of each other and disappear, and I have this, and that is the form of an additive representation. So this definition of a uniform system captures the notion of a structure that's parallel, and a structure that's parallel by this proof can immediately be transformed into one in which the indifference curves are straight lines, and that's what, of course, would arise from an additive situation. So now the question is, are there conditions that we understand for conditions for a system to be uniform? And there's a classic theorem due to Blackshay and Bowles that was proved in the 1930s that answers this question under a fairly strong hypothesis. And once we see the answer, it will become it's fairly obvious, given what we already know about conjoint measurement, that this is the correct theorem. We'll talk about a situation where there's a family of curves that passes or covers every point in the plane. That is to say, given any x and y, real x and y, that's a point in the plane, there is assumed to exist a lambda in this index set such that y is equal to f lambda of x. So there's an indifference curve that passes through every point in the plane, is what's being assumed. The assertion is that that family is uniform if and only if no two distinct curves intersect and the Thompson condition holds. Now, you can see why this theorem is probably true, given what we know. It's clear that non-intersecting indifference curves corresponds to independence. That's one of the things we had to assume. The Thompson condition was one of the things we had to assume for additivity. And that's being stated here. And now the rest of the hypotheses cover the other two parts of the usual theorem. The fact that every point in the plane is covered means you have unrestricted solvability, and the fact that you're dealing with a numerical system, of course, guarantees that the Archimedean axiom is correct. So you've got all the things you need for additivity in the theorem, and it's essentially what it's saying is if you've got a very strong form of solvability and you have the Archimedean condition, then there's nothing to check other than independence, that is, that the indifference curve not intersect, and that the Thompson condition holds. And that, of course, the Thompson condition is the hardest thing to check in this situation. That takes a certain amount of care. Now, this theorem was generalized in recent years by Michael Levine, and what he did was relax very appreciably the assumption that every point in the plane is covered by the family. And he instead assumed that he was dealing with a situation in which he had a finite number of indifference curves. And the results are contained in theorems 8 and 9 of Chapter 6. I won't describe them in detail. On the other hand, I will try to describe the general nature of the theorems. In this case of a finite number of indifference curves, it breaks up into really two situations. In the two situations correspond, as we've run into before, to whether or not what you're dealing with looks like the integers or whether it looks like the rational numbers. And if it looks like the integers, you get one situation. If it looks like the rationals, you get a situation that then can be, by completing the rationals just the way it's done in the real number system, you get the density of the Blanchet theorem. And so what Levine has done is considered these two cases separately. Theorem 8 concerns the case that looks like the integers. And what one means by this is the following. He takes any two of the family and considers the function that's constructed by first evaluating the inverse of the one and then applying the other. And this permits him to generate a whole additional set of curves in the plane in general. And the one case is that if all of these curves look like one curve being raised to powers, that's the discrete case that's analogous to the integers, and one can get an exact solution to the problem. However, it turns out that the function phi that renders the scales parallel to one another is not very unique. He's able to characterize the uniqueness of it, but it's not an interval scale, as, for instance, in the Black-Shea theorem, we are indeed dealing with an interval scale. The other case that arises is when these functions are not expressible as powers of a single function, but rather they continue to generate much in the way of rational numbers, and while they don't cover the plane, they come very close to it. They're in a sense in which they're dense in the plane. This is actually covering them, covering every point, whereas in the second case here, what one gets is a high degree of density. You've begun with only a finite number of curves, and you keep generating things sequentially from them, and you get a countable but dense set of curves. And then what he has to do is impose some assumptions, and these get to be quite technical, that permit you to fill in the remaining points in a systematic way such that this theorem then applies. And he is then able to show, using that theorem, that in fact the structure is uniform. The nature of those assumptions is, of course, again, that the curves don't cross. That's the independence requirement. And the technical assumption is that you're able to embed this countable system into an uncountable one in a systematic way. And that settles the problem of the finite number of curves. Now, the question of how one uses this information in particular empirical situations is much trickier, and that, while there's been work done on it, Levine has done considerable work on the problem. I think that the statistical data issues are sufficiently far removed from the main thrust of this set of lectures on measurement that I will not go into it any further. The last lecture on conjoint measurement will take up the problem of what you do in a factorial situation where you have only finite structures. Everything that we've been talking about involving some degree of solvability has been assuming continuous or nearly continuous structures, certainly infinite structures, whereas, of course, any data situation is entirely finite in character. And the problem has been studied, and we will talk about those results in the next lecture. That is, Professor Tversky will talk about them in the next lecture on finite conjoint structures.